Good afternoon, everyone. I want to thank everybody for joining us today. Appreciate you taking your time out. And today we will be discussing laser-induced fluorescence and integrated site visualizations. Looks like we have a nice mix of environmental consultants and regulators with us. Also, a few public and private site owners are joined, so welcome to everybody. My name is Ed Creaden, and I'm the Director of Marketing for the WCEC family of companies, and that includes Matrix Environmental. I've been an environmental consultant since the late 1980s, and a significant portion of my career has involved site characterization and remediation at petroleum sites throughout the Midwest and many other areas of the country. I'll be joined later in the presentation by Jim Roll. He's our Director of Environmental Services. Jim has an extensive consulting background as well, and one of his areas of specialized expertise is the development of 2D and 3D site visualizations at petroleum sites. So he'll be going over that material after I present some information to you about the LIF technology. First, we'll go over a couple of quick webinar logistics, and due to the number of people on the line with us today, it's really not going to be practical for us to do a live audio Q&A. But you will have access to the chat window to type in questions. So if you look there on your control panel from the webinar, you should see that chat window. And please feel free to go ahead and type in any questions as we go along, and we'll pick those up at the end. Also, if you don't feel like typing out your question, you can always contact us later, and we can talk to you individually. And finally, a recording of today's presentation will be made available to everyone that registered for the webinar. So let's go ahead and get started. Here's an overview of what we'll be discussing today. We'll go over the basic principles of the LIF technology and equipment operation. We'll show some examples of deployment of the instrument in the field. We will talk about the data output, including a review of the logs and waveforms produced by the instrument. We'll give a very brief overview of contaminant phases in the subsurface and talk about how LIF is used to delineate the non-aqueous phase liquids. We'll show some examples of instrument interferences and limitations. We'll talk about LIF data analysis and development of an LCSM. And finally, we'll go over a couple of recent case studies and show some examples of our 2D, 3D ISV deliverables. Laser-induced fluorescence. This is a term that most people here are probably familiar with, either from your own experience working with the tool or possibly from the recent ITRC LNAPL training events where it is frequently mentioned as a useful technology at LNAPL sites. There are two main types of LIF tools, and both of them were developed by Dakota Technologies out of Fargo, North Dakota. The ultraviolet optical screening tool, or the UVOST, was the first LIF tool developed by Dakota. It was initially used at a wide variety of petroleum-impacted sites, but they pretty quickly realized that the UVOST was just not performing reliably for NAPLs containing moderate to high PAH concentrations, so they developed the TARGOST technology. And the TARGOST is used to detect coal tars, creosote, and other heavy petroleum products with relatively high PAH concentrations. And the UVOST is now primarily used for sites impacted with lighter-end petroleum products containing low to moderate pH concentrations. Both technologies use lasers to generate a fluorescent response from PAHs present in NAPL, and we measure and evaluate that response in real time in the field. So this presentation focuses primarily on the UVOST technology, although many of the basic components of these two technologies are very similar. Let's look at the basic features of the UVOST. As I just mentioned, the UV laser excites the PAH molecules present in LNAPL, causing the PAHs to fluoresce. This is a direct sensing tool, meaning that it collects data from immediately adjacent soil and whatever fluid is present in the pore spaces of that soil. Unlike some traditional site assessment tools, it can identify the presence of mobile and residual NAPL, although it cannot differentiate between the two. Data are logged in real time, giving an instrument response versus depth. And we deploy the UVOST using direct push. However, some vendors may use the UVOST with CPT. And although we can get upwards of 500 feet per day or even more at optimal sites, we like to be a little more conservative in our estimates and say that we can generally get at least 200 to 300 feet of production per day. Of course, that's very site dependent. There's a lot of factors that can influence that, such as site geology, physical access limitations, the site cover such as concrete or asphalt, whether utilities have been cleared in advance, how often the field rep may need to call into the office for the client. All of those types of variables come into play when estimating the UVOS production rates. But essentially, if you can probe it, you can LIF it. And whatever circumstances you may have at your site that would inhibit or promote the use of a geoprobe, those will be your same limiting factors for LIF production. And when considering the density of data collected in an LIF study, the cost effectiveness of LIF is far greater than traditional assessment strategies on their own. The fluorescent responses of certain PAHs are predictable in terms of the wavelength and decay times, so this information can be used to not only identify the presence of LNAPL material, but also tells us something about the composition. And we'll show this in greater detail in a few minutes when we look at some waveforms and logs. Because some of the lower molecular weight PAHs, such as naphthalene, are highly fluorescent, diesel is one of the ideal LNAPL materials to be identified with the UVOST. But I'd also like to mention that monoaromatic compounds like pure benzene or xylene, they do not fluoresce efficiently, so LIF will not reliably detect LNAPLs composed of these materials alone. So a little bit about the UVOST equipment here. What you see on the left is what we call the SPOC, the shock protected optical compartment. And this is a very robust piece of equipment. It's hammerable, drivable with a geoprobe. It's got, essentially what you see is we've got fiber optic lines that bring the laser down along like this, bounce off a mirror and go out the sapphire window, and then come into contact with PAHs that are present right against the window, really. This diagram might be a little bit misleading in that sense. Then that fluorescent response from the PAHs is returned to the surface with this return fiber, and then it's processed with the optical screening tool. And you also notice on here we've got conductivity dipole, so electrical conductivity data are collected simultaneously with the fluorescence data. And on the right, we've got this is basically the control center. We've got a laser generator here on the top part. It's a gas-generated laser. And then we've got an oscilloscope here. And this is essentially used for calibration and the processing of the return signal. And then over on the side, you see a laptop sitting there. And that gives you a little glimpse on this little screen here of what the operator is looking at in the field while the probe is being advanced. It's giving real-time data. Waveform callouts and that sort of work is done right here on a computer screen. Here are some examples of deployment methods. We've got skid steer with the geoprobe connected to it. There's a little four-wheel drive unit here beside it, and inside this little weatherproof tent is where we've got the UVOST equipment. And what you really can't see here is on the back of this this little Kubota, there are the geoprobe rods, and they're pre-strung with the fiber optic cable. And then you also can't see there's a little cable that runs on the ground like this and comes into the geoprobe unit like that. So the two are connected that way through the cable. Here are a couple more examples of UVOST deployment. This is using a truck and track mounted unit at sites without any significant access restrictions. You can see a flatbed truck there with another four-wheel drive unit. And on that unit here on the support is the UVOST unit. Over here on the right, we've got a tracked unit, and it's got a handy little trailer that just pulls behind it there, and we've got all the UVOST equipment just right there. So it's very easy to move around and access. But we know not all sites are so simple. On the left, we have an example where we had to drop in our direct push unit using a crane to access the interior of an AST farm. And on the right, you see we have a unit on a pontoon ready to deploy the UVOST into sediment. Okay, so here's some outputs. The image you see here on the left is a 3D illustration of diesel's fluorescence emission. This is a pretty data-intensive representation of the captured fluorescent light. and it's referred to as a wavelength time matrix, or WTM. You can see the 4 wavelength channels of the UVOST represented by the colored lines going from left to right across the image, indicating intensity and duration of the signal. But the WTM can't be continuously produced while the probe is moving due to the tremendous amount of computing power it would require. So the optical screening tool samples the total fluorescence at these different wavelength channels and then optically delays the fluorescence pulses and records them with an oscilloscope, ultimately generating a multi-wavelength waveform, which is what we see here on the right. This waveform still allows us to see the intensity here along this axis and the duration of the signal, and it can be used to ascertain various properties of the LNAPL and compare one product type to another in the field. Also, I'd like to point out here the calculated color up in this little box here. That is what is plotted on the UVOST log for general identification of this particular type of waveform. Here we have typical waveforms of various unweathered fuels and oils. A brief look at these will pretty quickly show you how the lighter fuels tend to have higher responses and longer durations in the 350 nanometer wavelength. So that would be along here, really, those peaks there. While the heavier fuels and oils tend to have higher responses and longer durations in the 450 to 500 nanometer range. So now we're talking about along here, really these. I'm not very good at drawing with my mouse, so pardon the crooked lines there. At older release sites where the LNAPL has become weathered, you may see a shift in the waveforms more towards the right, and that's something we call red shifting. Our operators are really quite adept at identifying the subtle differences in these waveforms out in the field and examining the waveforms throughout the course of the project, and sometimes reveal the presence of commingled plumes or new or unexpected sources at a site. And LNAPL samples obtained from monitoring wells on a particular site can be placed directly on the UVOST before mobilization or during the course of the field work, and that allows us to check the instrument response and the characteristics of that specific material. So that's a pretty handy thing to do. We usually recommend that people send us in some of their product before we schedule a site if there's any question about its ability to be examined with this tool. So let's walk through the major features of an actual UVOST log. This gets generated live before your very eyes while the probe is going into the ground. Here we have depth is on this vertical scale here, and the fluorescence intensity is here. Essentially, the more petroleum that's present in the soil pores that are adjacent to the probe, the stronger the recorded response. So that, I think you can see pretty intuitively right here. As it comes out, we've got more intense responses in different locations here. So before each new boring, a reference emitter known as RE it's essentially a calibration standard, is placed directly on the window of the instrument to set calibration. And the RE contains a mixture of fuels including gasoline, diesel, kerosene, and other oils. And then that calibration waveform is put on each log right here. I just drew through it, but if you can see right here, it says 100% RE. So that's the standard that basically all of the data are normalized to. So you'll see results that are represented as 2% RE or 100% RE, or in some cases you might even have 500% RE, but it's all relative to that particular calibration standard. The waveform callouts can be produced for any interval in the boring, and the product type can be generally determined from these callouts. So this is a qualitative evaluation. That's what this little box here represents. And if you can see, maybe I should clear some of that off of there. Right here, these heavy bars are indicating this is the interval that this waveform has been called out, so we can examine that. This is a very qualitative evaluation here. Now notice also there's a correlation of EC. This is the electrical conductivity here, and you can see as it's going along with depth, there's some pretty fine-grained material here. It gets into more of a coarse-grained material, and here we have a nice correlation with where the LNAPL is hanging out, and there's a little nub right here that may not have had as obvious of a connection there to the lithology, but this is useful to have this electrical conductivity data. We found that it can provide a more objective and complete data set than might be obtained from a typical geological description of a soil sample during a routine site investigation. And then on the far right here, we have, this is basically the rate of push, and that is expressed in inches per second. So down here, if you can see this little scale, that's the 1 inch, that's a ½ inch right here before it. And the idea is to try and push this, the instrument at an ideal rate of 0.8 inches per second. So this allows us to monitor that rate of push. So to put the use of the LIF tools in context, let's take a moment for a very brief review of hydrocarbon impacts at petroleum release sites. We obviously don't have time to go into a lot of technical detail here, and most of you probably don't need that, but as all of us that have worked on petroleum sites know, each of these 4 phases can exist at a site in varying degrees, and it can be extremely difficult to complete a risk assessment or develop an effective remedial approach if we can't differentiate source material from the other phases of contamination. When you consider how non-specific headspace screenings and lab analyses can be with regard to contaminant phase, relying on these data alone makes development of an accurate LCSM quite difficult. So in this illustration, we see the primary fate and transport mechanisms that affect the migration and distribution of petroleum in the subsurface. So upon release, the LNAPL infiltrates the unsaturated zone, predominantly under gravitational forces. A fraction of that product is retained in the soil's pore spaces due to interfacial forces, leaving what we know as residual saturation. A portion of the LNAPL that migrates to the capillary fringe may spread horizontally, but again, as we know from advances in LNAPL science in recent years, LNAPL does not float on the water table in a uniform high saturation pancake layer. It preferentially moves through zones of greater permeability, and depending on the head pressure from the release, it can be forced well below the water table. Shortly after LNAPL has been released, then we have volatilization occurring, and that results in soil gas vapor impacts, and advective forces distribute aqueous phase contaminants in groundwater. This inset box here illustrates soil gas vapor contamination present in the pore spaces of soil along with individual molecules absorbed contaminants. As most hydrocarbons are multi-constituent mixtures, concentrations in soil gas vapor depend primarily on the composition of the LNAPL. And looking closely at this inset, you'll notice there is no LNAPL represented in this part of the diagram. Where LNAPL saturation exceeds the residual concentrations, mobile NAPL is present. So in the non-aqueous inset box, we have an illustration of mobile NAPL, which is hydraulically connected within the soil pores. But the soil pores are never really 100% filled with LNAPL. That saturation depends on a lot of variables, including the geology, the LNAPL fluid properties, and various release dynamics. In the bottom inset, we illustrate how all 4 phases of contamination may coexist in some areas of the site. So you can see here we've got little globules of NAPL here. There's some aqueous phase, there's some soil gas, sorbed contaminants, everything here all together. The standard NAPL assessment methods. These are what many of us have used for many years. Soil boring investigations, monitoring well networks, vapor surveys, direct sensing tools such as the MIP. All of these respond to all 4 phases of contamination. So it's pretty tough to differentiate LNAPL from other phases of contamination using these tools alone. But we've got some good news for you here. The UVOST responds only to LNAPL. That allows us to map out the LNAPL body for development of a reliable LNAPL conceptual site model, which is essential when performing our risk assessments and remediation. And also, to develop a good comprehensive conceptual site model, previously collected data from standard assessments is very useful here too, including historical and present land use, geology, soil and groundwater chemistry data, And these are all used to guide the UVOST investigation planning and also in the development of the model itself. So we never like to try and leave the impression that we think that the UVOST is the only tool you need to go out and use at a site, because that's certainly not the case. Here's a diagram, just kind of a conceptual diagram showing a site being assessed with a UVOST. Just using this to really point out that we can access some tight spaces here. It works equally as well in the unsaturated or the saturated zones. The UVOST borings, we typically recommend that they're conducted on a grid pattern across the site. So you can see 3 borings represented here, and we've got the nice little clocks to show you they're maybe an hour apart to do those. And we usually recommend thinking about a 25 to 30, maybe 35-foot grid, but that can vary greatly based on site conditions, the size of your site, and other things that you already know about the site. Here we've imposed a very simplified UVOST log. You saw an actual log earlier, and this is just a little visual snippet from that to show how the data correlate with mobile and residual LNAPL encountered in the saturated and unsaturated zones. Now keep in mind here the instrument will only respond to mobile or residual NAPL in soil that comes into direct contact with the instrument. So that I think is illustrated pretty well here. As you see, it's moving along here with depth, and we've got no response, and we hit this little nub of residual right here, and we get a little correlating response and so on. So you can see as we come down beside the residual NAPL body, there's no response on the log. And then it starts to tick up a little bit as it's on the edge of the NAPL. And then we get a nice, once we're in the real body of the mobile NAPL here, this zone here, we get a really nice intense signal. And then it tapers out, and immediately below, that lines up maybe, coming down this way, then there is, again, no instrument response. So we typically recommend going about 10 feet below the water table, or what you believe to be the greatest depth of LNAPL, to ensure that the LNAPL is adequately characterized with depth. We also recommend at least 1 boring at every site go about 20 feet below the anticipated depth of LNAPL. And this is because our experience has shown us that it can be a lot deeper than initially expected. You just may be surprised when you do this. And if that information was missed, it could have some pretty serious impacts on the effectiveness of your remediation. As I mentioned when I showed you the example of a UVOST log, at any time during the investigation, the client can request a waveform callout from any sampling interval. And here you can see the waveform callout for the interval indicated by the thin little pointer coming from the callout box here. And on this example, we see a typical diesel waveform, and the calculated color from that waveform is represented on the log. I know it's very small, but that's that little calculated color I showed you earlier, and that's what's appearing here in the body of that signal response. And our operators, they routinely examine these callouts during the assessment so we can help our clients understand what they're seeing in the field. Here we have, this is intended to be kind of a commingled area here between the gasoline LNAPL plume on the right and diesel on the left. And so again, we have a very a pretty thin zone of NAPL here that's represented here by that hit. And if you're really watching closely, you can notice there's a little bit of a change in these waveforms. If you look at the blue and the green peaks there, you'll see it changed just a little bit. They're equal height there, taking on just a little bit of a different relative intensity and duration, and the waveform is taking on a different calculated color as well. That helps us differentiate between materials on the logs while we're in the field. And then over here, when we're really in the pure gasoline LNAPL, now the waveform box here takes on this very typical stair-stepped appearance of gasoline waveform. That calculated color is represented here in the blue. And this a good thing to point out here is obviously you would expect some soil gas vapor impacts here right above this LNAPL body. And again, this technology is not going to respond to that. So it helps us clearly identify the NAPL from the other phases of contamination. And that's again true down here in the saturated zone below the LNAPL body, where we would certainly expect to see some aqueous phase impacts. And we all know that real-world sites are never like the fish tanks filled with lab sand and the experiments are conducted in, the small-scale subsurface heterogeneities that can go undetected using conventional investigation strategies are really quite often very complex, and they can cause abrupt changes in the LNAPL migration and distribution over very short distances. The UVOST's gridded sampling approach and the density of UVOST data collected vertically appropriately characterize the heterogeneities that control contaminant distribution, transport, and fate. Data density determines how clearly you will see the picture, and subsequently how accurate your LCSM will be. This is somewhat analogous to the amount of pixels in a digital image. As you can see here, we only have enough pixels to tell light from dark areas, and this information is really pretty useless to see what we've got going on here. But as we add pixels to our image, we have a more clear idea of what we're looking at, and we can pretty well outline our main area of interest. When it comes to effective and efficient remediation, this level of clarity is really essential. And when we really crank up the resolution, we can now see very clearly what lies in the area of interest, but was it really necessary to go to this level? We may now have a solid outline of our subject, but when the finest details were still unknown in the middle image, we were still quite confident that our main area of interest took on that same shape. So there's really not a lot of difference between this or this. And the same can be certainly true for remediation. There's a limit to how much data you need to effectively clean up a site. And quite often we assist our clients in developing an appropriate sampling plan, sampling strategy with the UVOST to maximize their productivity, their cost effectiveness of the assessment, and really help avoid any unnecessary costs. And how well the UVOST sees certain types of products depends on the soil type and the age of the release. For example, weathered gasoline and clay can be more difficult to detect. However, diesel is not affected to the same degree by soil or age and fluoresces very well. Other materials that you see here in this list are very amenable to assessment by UVOST. And again, we're noting here that the tar ghost is used for detection of materials containing higher concentrations of pHs, such as the coal tars, creosotes, heavy crudes, and tank bottoms. Here's a list of commonly occurring substances that the UVOST does not detect. One item of note here, though, is that Dakota Technologies is in the beta stages of developing a technology they call dye LIF, and it has had some very promising early results detecting chlorinated hydrocarbons at DNAPL sites. So you may check out the Dakota Technologies website to learn a little bit more about that emerging technology. It's certainly something to watch for here in the near future. And here's a list of materials that can cause false positives with the UVOST. We've got different organic materials, seashells, calcite, calcareous sands. Up here in the top part of this particular diagram, these are different sands from different places around the world. Actually, these first two are. I think the second one is tree roots. Here we have, this is considered normal background response. This is, if you change the scale on a log, you're going to see that very, very commonly. But usually false positive waveforms, they do have distinctly shorter lifetimes, and they appear somewhat odd relative to LNAPL waveforms. So to discriminate between the interfering fluorescence and fluorescence caused by true NAPL, we'll look at the waveforms retrieved in the callouts. And also, you may be able to tell here how many of these waveforms look distinctly different than those we showed you on our previous slides, where I listed the jet fuel and the gasoline and whatnot. But in cases where the differences between a false positive and actual LNAPL at a site may be more subtle, we'll turn to other lines of evidence and site knowledge to help us sort out the false positives from the true LNAPL responses. So that concludes my part of the presentation. I hope this was useful for you to learn more about the principles of the technology and how it stands apart from other site assessment tools, and how it's used at LNAPL sites. I'm going to hand the controls of the webinar over to Jim, who will show you some examples of 2D and 3D visualizations that we prepared for a couple of UVOST sites. Just take a moment to do that. So if you can bear with us for a second, Jim will resume here in just a moment.
All right, hello everybody. It's Jim Roll talking, and yeah, now that you've seen a lot of what we do as far as data collection goes and what type of data you get, you may be wondering, what do I do with all this great high-resolution subsurface data? And one of the things that we've developed over the last year or two is what we call integrated site visualizations, where we take the LIF data in conjunction with all the site data that you may have, be that high-resolution aerial photography, AutoCAD maps, ArcView features, things like that, to bring a real 3D representation of the site to life. And this is an important component of the LCSM development. It really helps all parties involved in a site understand what's important when you're talking about contaminant distribution, fate and transport, and remediation. So some of the typical components that are in our ISVs would be high-resolution imagery, the traditional base map features we talked about, topographic maps, aerial photographs, and nowadays we use a lot of LiDAR data, so you can get a better feel for topography at a site that has an LNAPL plume beneath it. Now, this slide is a pretty typical ISV deliverable. This has a lot of components. You can see we've got an aerial photograph that is overlain on a geologic surface. You can see we've got a sand and silt layer. Those are identified using the EC probe. And then we have a 3D plume shell with a slice, is what we call, cut through that, which is this area of a slice through to reveal an inner intensity within the 3D plume shell. And then below the 3D plume shell we have a two-dimensional projection. It's a two-dimensional isolate concentration plot. So this just helps to visualize not only the extent in 3 dimensions of this plume and how that relates to surface features, potential third-party impacts, things like that, but also an intensity of maybe where you would start thinking about targeting your remedial efforts at this site. Okay. So this slide, we've got a little bit of a more interesting view. This is the same 3D plume shell that we were looking at in the previous slide. This time we've taken that plume and cut some cross sections through it, and within the cross sections you can see the plume intensity again. You've also got the EC data. So here you can see this scale bar actually shows the percent RE, with blue being the lowest percent RE that was a true LNAPL hit, which the threshold here you can see was 2% RE, up to the maximum hit at the site, which was greater than 301% RE. Another static deliverable from the same project, this is actually a fence diagram that's similar to the one of the cross sections you just saw. This one is interesting. We did a high resolution characterization of the subsurface coupled with a super accurate survey of the ground surface at the site to give us a depth of each NAPL interval and an accurate depth of this geologic interface that you can see along where the sand and silt layers are exploded. What that allowed us to determine was that the NAPL migration at this site was actually dictated by the slope of that interface, and you can see that it slopes in this view from the right side of your screen to the left side of your screen. So this kind of data at this kind of resolution was something that was previously unattainable without this tool like the UVOST. Again, our deliverables include static images like the ones you're just looking at, digital animations, which we'll look at a couple in a minute, and a dynamic 3D file with an interactive viewer, which are called a 4DIM. The 4DIM, you can take basically any view from a site, manipulate the 3D file, look at it from all angles, and then produce your own deliverables that are relevant to your site. These deliverables really help to prevent misconceptions that traditional data sets would give to regulators or clients, so on and so forth. So this is one of our animations, and I'll just kind of narrate this. A lot of the components of our ISVs are shown in these animations, and they're really kind of a neat way to get a handle on what's going on at the site in a couple minutes. So I'll just hit play on this and narrate through it. You can see we've got the borehole grid there, and if this is a little glitchy, it could be the internet connection that you have, but it should be still a usable view. You're going to see we've got, I'll pause for a second. You can see we have now a 3D plume shell that is projected into the subsurface. We have aerial photograph, we have AutoCAD features that are all geo-referenced. You can see we've got utility corridors, property boundaries, things of that nature that are relevant to the decision process that's going to be made at this site. I'll play again. We're just going to rotate through a couple of views here. More of a perspective view, and you can see the geologic layers that were identified with the EC probe. Now the signal response, we're going to work through low concentration to high RE. So in essence, we strip away the shell to the core, and then we'll go in reverse and rebuild that plume shell. You can kind of see the areas of most highest intensity back to lowest intensity, which is the extent of the plume. You can also see we've got all of our boreholes represented with what we call borehole tubes. This view is a slice that goes vertically, top to bottom and then bottom to top, to reveal the inner intensity at depth. So you could, if this was an interactive 4DIM, you could pick the slice that you thought was valid, say at the soil groundwater interface, and see what the intensity of the inner plume was at that depth. This is a similar view that is cutting horizontally, so this is kind of like a moving cross section. Now we'll explode the plume at that geologic interface, at that horizon change. We can actually use this kind of data to calculate an estimated LNAPL contaminated soil volume in each geologic layer and in total for planning purposes for, say, a remedial excavation. And then we usually return these back to a map view showing all the relevant features. This animation is from a project. It's actually the static deliverables that we looked at a little earlier. The same project in Minnesota. Is a gasoline station that had a catastrophic release. The NAPL plume went off in a few directions as dictated by the lithology, as we explained earlier. A lot of third parties involved. I'll just hit play on this and we'll see again that you really get a clear picture of what's going on with contaminant, particularly LNAPL distribution at a site. Again, this is a 2D projection below the site. Now we're going to build the 3D plume shell from highest intensity to lowest intensity. Now we will bring in the lithology. You can see a slice revealing that inner intensity we talked about. And then some views illustrating the distribution of LNAPL in each of those geologic layers. And just a few rotational views so you can see the inner intensity. And then again, typically we conclude these animations with kind of a relevant shot of the site. So now let's move on to a case study. This is one of my projects up in Montana. This is a legacy petroleum release site in downtown Polson that had initial investigation beginning in the early 90s. There's 13 different facilities in the area that are PRPs with identified releases. There's a large undefined NAPL plume. We had NAPL present in various monitoring wells across the site. There really was never a definitive answer of the distribution of LNAPL, and we had a complicated fine-grain barbed lakebed sediments that proved to have some tricky transport mechanisms that the UVOST we thought would really help us understand. There's a sensitive surface water receptor involved, which is Flathead Lake, and this is on the reservation. It's a site that is administered by the Montana DEQ Petroleum Technical Section. However, there's plenty of parties involved, as there are with lots of sites. Here's just a map view of the project area. Kind of the epicenter of the release area were these facilities that I'm drawn in red. That's called the Four Corners area, where there was 4 high-volume petroleum, both gasoline and diesel distribution operations. Most of the other PRP sites that are outlined were heating oil tanks, and there was one other high-volume petroleum distributor that had some potential issues associated with it. So we developed, in conjunction with the DEQ, plan to go investigate this site using UVOS technology. Let me clear this off. I'm a little... There we go. So this investigation included 138 UVOS borings completed over a 10-day period. So when you worked out the numbers, we were getting about 500 feet a day. This is a pretty ideal site for the UVOS equipment. We recorded geospatial data points for each boring using a sub-decimeter GPS. So we had XYZ data for all of our boreholes. And then we were doing daily uploads of all this data, including the UVOS and GPS data, using our real-time data transmission service. This allowed us to have our LIF UVOS analysts provide daily updates with a 2D LNAPL isolate concentration map. We use those maps in the field to guide the investigation to make sure that we are delineating this plume in all directions, horizontally and vertically. And then the depth of the borings was also correlated to the high and low pool lake elevations of the adjacent Flathead Lake. So here you can see our investigation area and our boreholes, some of the existing free product monitoring wells that we had at the site. And then you can see this is a 2D isoconcentration plot of our results. You can see we have some of the red areas relate to the high intensity LNAPL zones, which correlate to the locations of the high volume petroleum distribution operations. And we have a northwest trending plume, which is what we had anticipated based on our historic site data. And then extended down towards the lake, where it eventually became a a high concentration dissolve phase. Now, this is a map view of the 3D plume shell. You can see there's always a little difference between the 2D shape and the 3D shape from above. And that has to do with the way the data is processed. Essentially, in the 2D, you're flattening 3D data into a 2D projection. From here, we're going to show a perspective view to show the distribution at depth. This is kind of a neat view. We have LiDAR. We have this aerial photograph tied to the LiDAR surface, so you can see the slope going down to the lake, and you can see the plume shell extending underneath buildings, roads, lots of third-party issues here. And this is an example of a deliverable that with the 4DIM player, you could have any of these views at your discretion to provide in your report for your site. Here's a kind of a cross-sectional view. If we rotate this one even further, you end up with this cross-sectional view. In this one, we've extended the elevation of the Flathead Lake high pool and low pool. And what's really interesting with this that the UVOS allowed us to determine was that the LNAPL distribution vertically was dictated by the high pool and the low pool levels of the lake. So what did we do with our data? We used our data to determine a remedial strategy that is going to be installation of LNAPL recovery wells and eventual LNAPL transmissivity bail-down testing. We targeted areas of high concentration LNAPL or continuous larger LNAPL bodies for the installation of wells, and that work's going to be ongoing this winter and through the spring. So in summary, this investigation successfully delineated the extent and magnitude of the LNAPL plume, and it allowed for the targeted LNAPL recovery. We completed this in 10 field days with a total cost of under $100,000. Less than half of that cost was the actual UVOS unit with operator and the geoprobe unit with operator, and then the ISV reporting, project management, our field oversight. That's all included in that since it was our project. Previous investigations at this site before we had the project totaled over $1 million and were not successful in delineating this plume. So that's a good example of how efficient you can be with the LIF technology. And again, it greatly advanced our LCSM through the collection of this detailed data. So with that, I'm going to ask if anybody has any questions to go ahead and send those in now. And then also, if once we have questions, if you would like to have links for our videos or for an example 4DIM, if you could send either myself or Jim Zube or Ed an email, we can get you the links so you can have those files to look at on your own computer in your own time. So I have a question here, it looks like, about the typical cost of a UVOS investigation. And it's probably the most simple way to answer that question is that, it varies site by site, but without mobilization, the UVOS unit with operator and a geoprobe unit with operator runs about $4,000 to $4,500 per day. And we can get you a detailed cost estimate based on your specific site needs. But I would plan on 300 feet a day of production depending on geology, and if you've used geoprobes enough, you kind of know what kind of guidelines you're looking for there. Okay, here's another one that's asking about the correlation of LIF data to traditional lab samples, soil samples. The correlative lab samples, there's a couple different ways to look at that. We don't typically recommend the approach of trying to correlate, say, a % response of LNAPL to a part per million hydrocarbon in soil. And there's a few reasons for that, but the LIF data is in a nutshell, it's very high resolution. So it may be detecting LNAPL bodies, residual LNAPL bodies that are in contact with the window that exist in a heterogeneous state in the soil that a typical soil sample by comparison is essentially a compositive sample where you would have some smaller area of that, say 8-ounce soil jar that contains LNAPL and maybe some majority of that sample that does not, and you pack that in a jar and send it to the lab, and you may get a result that doesn't really represent the whole picture of the site with regard to LNAPL distribution. And the other side of that is that once we establish the waveform that's relevant to the site and the percent RE that's relative to the site, you may have a 2% RE that is LNAPL. And that's just as valid as a 50% RE that's LNAPL. They're both LNAPL. They're both going to cause you the same problems. And the percent RE can be a misleading way to look at it if you're looking at an absolute percent RE. So the important thing to remember there is that if you detect it with the LIF, it is LNAPL. And that LNAPL is going to keep that site open for years to come if you don't deal with it directly.
Jim, I see another question here asking about the data callouts. Essentially, the question is, are the data callouts only available to be selected real time, or can they be selected after the field work is completed? And the answer is they certainly can be selected after the field work is completed, so there's no problem there. And also, there's another question about how does the data for a weathered plume compare to that for a recent plume? I think that, you know, if you use gasoline as an example, it's really something that's probably more impacted by weathering than diesel fuel. And if you recall when we were looking at the slide that showed the different intensity and duration of signal on the 350 nanometer wavelength, which was represented by the blue spike, I mentioned the term red shifting earlier. A lot of times we will say, as we see a material that has weathered, it has somewhat red shifted because those lighter components of the petroleum may have volatilized out or otherwise are just degraded, while the heavier, more persistent components of the fuel mixture will still be there. So if you, you know, it really depends. I mean, if you have a site that's had multiple releases and you see, and you know it's from the same material but different times, you might be able to do a little bit of, you know, what would the word be? Kind of, you know, the correlation between, because where you see kind of the more red shifted signal compared to the fresher response. So hopefully that answers your question there.
Yeah, another thing there, another thing on the weathering and some of these site-specific signatures. You know, typically when you get to a site, what you want to do is go to an area where you know you have LNAPL and advance a couple of holes there. And that's going to give you kind of a fingerprint of what that product that you have at your site is doing in that particular soil type. And to compare site to site is pretty tough to do. So once you get that signature for your site, you're going to be able to track that signature site-wide. And that's something we did like at the Polson site. We knew the type of signature that we were looking at. And it was a weathered gasoline, and it did have a commingled diesel and heating oil. And actually the signature, if you were to just take it out and look at it in a vacuum without any other site knowledge, looked more like a kerosene signature. But we were able to correlate that particular signature to the high volume petroleum distributing operations, and we saw that signature throughout the majority of the site. So it's really a site-specific effect that weathering has, and our operators are really good at determining what that signature is and when they're seeing it across your site.
Yeah, very good point. Another question I see here is, Can this technique distinguish between commingled plumes of different materials, such as gasoline from one site and diesel from another site? I think that, that the conceptual diagram I showed earlier, where it was an illustration, kind of a cross-section showing a diesel plume off to the left and a gasoline to the right, one of the things that I was trying to point out there is how the instrument's response changes as it goes from just when we were in the pure NAPL, or the diesel LNAPL, and we got into the little commingled arms of those two plumes, and we had a different representative color that was coming up in the waveform on the log, and we also had some subtle but apparent differences in the waveform callouts where those were commingled. And then when we went over to look at the response in the gasoline area, we had much more of that classic stair-stepped gasoline response, and the representative color was more towards the standard for gasoline. So I hope that answers your question there, John, but feel free to contact me if I miss the mark of your question there. And Jim, one more, I'll jump in. I see, does 100% RE correlate to NAPL saturation? And I think the answer to that is no. Basically, 100% RE is saying that the intensity of that signal is equal to that of the standard that was used to calibrate the instrument there. But we can get much higher responses than 100%, and we can have mobile NAPL that might be appearing as 5% RE in different areas, because that RE is a mixture of different oil products that's used to calibrate the instrument across the various wavelengths. But that mixture may not really be the same as what you have at a site. So you might have pure gasoline at a site that is only going to show up as a small percentage of the RE.
Another quick point on the saturation. LNAPL saturation is really the only way to determine that is with a transmissivity test. And like for example, we've had sites where we have 10% RE and it's gasoline, which doesn't respond as well in a fluorescence way as diesel does. Not that it doesn't respond well, it's just the percentage isn't as high. So for example, you may have a 5 or 10% RE right next to a well that you can produce 30 gallons a day of LNAPL from with a 17-foot column of NAPL in it. There's a lot of things that go into the recoverability of NAPL and the saturation of the soils that are not related to percent RE. Percent RE is really dictated by the type of product, the weathering of the product, and the geologic conditions that product is distributed throughout.
Jim, I'll let you field this one. There's a question from Nancy. Can UVOs be used in directional drilling / push methods?
Boy, that's one that, I would assume Randy could come up with something to make that work. It is hammerable. There isn't an application that I know of that they use directional drilling with the unit.
Yeah, and we'll look into that a little bit more, and if we learn after the webinar here that there are some applications for directional drilling, we'll send you an email on that, Nancy, and let you know what we learned about that. But yeah, I'm not aware of that having happened before. But really, if you envision a drilling scenario with a geoprobe direct push type of unit, that is where we can put this. And again, there are other methods of deployment out there, and such as the CPT. But yeah, I'm not really familiar with other like directional drilling that I've done, at least in my past, how UVOs could be connected into that type of scenario. Well, it looks like we're out of time. I think that we'll go ahead and close down here. And if anybody has any other questions, please do feel free to contact either the names and numbers you see there on your screen, Jim Roll or Jim Zube, who's our LIF Services Director. Feel free to send emails or pick up the phone and give us a shout. We're always happy to talk with you about a site and see if it might be something that this technology would be applicable to. At the end of when we disconnect here, you should be seeing a very brief survey about the webinar, and it's helpful for us if you take about 30 seconds or so just to click an answer onto the 3 short questions that should appear. If they don't appear on your screen as you shut down, then I think they will appear via email, so sometimes that's a little unpredictable for me. But either way, thanks everybody. We really appreciate your attending and look forward to talking to some of you in the future.